The molecular formula for this one is C10H12O2. That gives us 5 double bond equivalents. In the spectrum I see a 5H and it's between 7 and 8. That would indicate an aromatic ring with 5 hydrogens on it. This one here, C6H5. We've got a CH3 group over here and 2 CH2 groups over here. You can see now this is all counted down to 1 C, 2 O's and 1 double bond equivalent, suggesting we have a C double bond O and an oxygen. Now everything's counted down to 0. We can put the structure together. The 2 CH2 groups. This CH2 group has 3 peaks. That indicates it's next to something that has 2 hydrogens. That is probably another CH2 group. This one also has 3 peaks, so it's next to 2 hydrogens as well, which suggests that the 2 CH2 groups are likely together in the structure. So I'm going to put them together down here. Now we have to figure out where the rest of this goes. I know that the CH3 does not go here, because if it did, this CH2 would couple to the CH3 and this CH2. Also, this CH3 would not be a single peak like it is here. So we know that CH3 must be away from the CH2 groups. So the possibilities now revolve around where this C double bond O and O go. They have to go together essentially, because the 2 CH2 groups have to be together, and we know the CH3 can't be next to the CH2. The other possibilities might have the C double bond O and the O down here, but again that's going to leave us in the same situation with the CH3 group not being by itself. So really all we're left with is this kind of situation where the CH2 groups are connected to the aromatic ring and the C double bond O and the O are here, but we recognize of course that the C double bond O and the O could be in either this order or in this order, and we have to figure out which one it is. So if we look at the discussion that I have here in the tip sheet, we can see that when things are connected to oxygen, for example when the CH2 here is connected to O, it appears at 4 ppm. When this CH3 is connected to O, it appears at 4 ppm as well. Any groups attached to C double bond O, for example the CH3, will appear somewhere between 2 and 3, and this is the same as is true in this situation as well. The CH2 connected to C double bond O is between 2 and 3. So looking at our example, what I would want you to see is that the peak at 4 ppm is a CH3, indicating that it must be connected to the oxygen. Had it been this way, this CH3 peak here would have been down around 2 to 3, and this CH2 would have been up around 4. But since we know that the CH3 is at 4 ppm, then we know it must be connected to the oxygen, and this must be the structure that we're looking at.